Hi, I'm Dr. Jim Zoval, a professor of chemistry at Saddleback College. You're about to watch one of my video lectures. If you like this lecture, you can get the entire Allied Health General Organic and Biochemistry course from the website address you see on the screen right now. Be sure to type the underscore between VOD and pages in this address. Enjoy the video. Chapter 9, we're going to talk about acids and bases. Before we talk about acids and bases, we have to understand this concept of chemical equilibrium. You guys learned about thermal equilibrium. Remember you did the lab where you took hot metal and you put it in cool water and the metal temperature went down and the water temperature went up until they were at the same temperature. At that point they were in thermal equilibrium. Not one or the other is going to get hotter or cooler. They're at equilibrium. They're exchanging energy at the same rate, so they're staying at the same temperature. We have to understand this concept of equilibrium before we could really get this concept of acids, bases, whether a solution is acidic, whether a solution is basic, sometimes called alkaline, and whether you should spend a bunch of money on this stuff that people are trying to sell you called alkaline water. I don't think so. Up until now, when we saw a chemical reaction, we had reactants getting converted into products. Let's say molecule A reacts with molecule B to make molecule C and molecule D. We did stoichiometric calculations. We said, okay, we have an unlimited supply of B, we got a certain amount of A, how much C and how much D can you make? And we assumed that this reaction just kept going in the forward direction until we ran out of A. And we based how much C and D would make on how much A we started with. That's what we did in the past. Well, there's more to the story. Many reactions are reversible. Here's what I mean by that. For A to react with B, molecule A has to collide with molecule B. At that point, if they collide with enough energy and at the right alignment, the right angles, old bonds can be broken and new bonds can be made. And in this case, they fall apart into two new molecules, molecule C and molecule D. Well, I hope it makes sense to you that once you start building up a bunch of C and D, let's assume this is a closed vessel, and you start making a bunch of C and D, molecule C can react with molecule D, collide with it and react and made back into molecule A and B. That's what we mean by reactions are reversible. Products can get converted back into reactants. Right, a reverse clock. Let's consider this reaction as an example. N2O4 is a colorless gas. There's a closed tube. It's a colorless gas in here. This reaction won't happen at an appreciable rate when you keep this N2O4 very, very cold. So you can keep it very, very cold, and the reaction's happening, but just so slowly you'd have to wait around for years and years for you to notice anything happening. But take it out of, say, a refrigerated system and let this start to warm up, and this reaction will occur. N2O4 will start to get energy, right? And how does this get energy? It moves faster, it's moving faster, it's vibrating faster, and you could break this nitrogen-nitrogen bond if it gets enough energy. How would it get that? Molecules collide into it, right? Or it's moving faster. You could break a bond. And N2O4 can break apart into two NO2 molecules. Chemical reaction, right? Decomposition reaction. This is easy to observe, and it's easy to measure also. If you have a device that can measure the absorption of light, you could measure how much of this is around and how much of this is around. And you see after a while, you start to see some brown gas being made in there. So at this point, you have some of this around still and some of this around. Notice the reaction is reversible. What can happen is two NO2 molecules can collide at the right angle and with enough energy and make another nitrogen-nitrogen bond and get converted back into reactants. So we say the reaction is reversible. Reaction proceeds in the forward direction and in the reverse direction. See how at first we labeled these reactants and we labeled these products and we considered reactants go to products, period. We're learning the rest of the story now. Reactions are reversible. So what we call reactants is just arbitrary. We choose to call reactants the stuff we write on the left-hand side of the chemical reaction. We choose to call products the stuff we write on the right-hand side of the reaction. If we plot in time here the concentration of each of those two species, the concentration of the stuff we started with, N2O4, and the concentration of the stuff we started to make, NO2, let's see what that would look like. So I could think of this axis as either concentration or amount of the material. And this, let's see what happens in time. So initially, we're at time equals 0, we're going to have a whole bunch of N2O4. And then we're going to see as time goes on, it starts to react, get converted into NO2, and we'll see the concentration go down. For NO2, we're going to see the concentration start at 0, but as the N2O4 starts to decompose, we're going to see that concentration increase. I plotted the concentration of N2O4 with a blue line and the concentration of NO2 with a yellow line to match those colors up there. People could do this experimentally. These two molecules absorb different parts of the visible spectrum, and if you have an instrument that monitors that, you could actually make this measurement in the laboratory. And when you do, it looks something like this. Notice, originally, at time equals 0, you have a lot of N2O4, and then as it starts to react, it starts going down, and you start to build up NO2. Notice, though, that this blue line doesn't go down to 0. It doesn't all get converted into NO2, because as it starts reacting, and you start to have more and more NO2 there, there's a higher probability of an NO2 molecule colliding with another NO2 molecule and getting converted back into N2O4. Look at what happens over here. See how these lines are flat? They're no longer going up or down. That means the concentration of the reactants and products are not changing. It's just staying the same. Does that mean the reaction stopped? No. What can we say about the forward and reverse rate at that point? They're the same, right? Right here, we're in this box, at some time, the concentrations of reactants and products don't change. They're constant. Just like with thermal equilibrium, the temperature didn't change. Here, the concentration of reactants and products don't change. That's chemical equilibrium. The rate of the forward reaction is exactly the same as the rate of the reverse reaction. The reaction at that time has reached equilibrium. I have an analogy, and it didn't work too well on the previous class. It was a basketball analogy. And no one really knew much about basketball in that class. Maybe you guys do. It goes this round ball about this big, and they throw it through this metal hoop, and there's a net, right? We have a team here, Lakers, right? Clippers. They used to be San Diego years ago. Right. Well, okay, so you know about basketball. Total players on the court, just the players, not the refs. Total players on the court at one time during the game is? 10. Are they the same 10 players all the time? What happens? They switch off. So you got the starters coming out, but you got the subs coming in at the same rate. So it's kind of the same thing. The total number of players aren't changing, but they're coming into the game and out of the game at the same rate. $1 million salary player equilibria, you could call it, or something. Did you guys see the movie? If you like the movie Matrix, is it Matrix or The Matrix? If you like the movie Matrix, you'll like this movie Equilibrium. In any case, at equilibrium, at chemical equilibrium, the rate of the forward and reverse reactions are the same. And the concentrations or amounts of the reactants and products do not change. Even in a gas phase reaction, you can still have concentration, say molarity, right? Number of moles per liter per volume. In the reaction we saw for N2O4, if you're able to measure those concentrations, at equilibrium, it turns out that we could use the following equation. See these square brackets right here? You haven't seen these before. That means concentration of NO2. Those square brackets in chemistry means concentration of NO2. And we saw about 5 million different concentration units, right? The concentration units are molarity, moles per liter. So when you see the square brackets, read concentration of NO2. Remember, at equilibrium, reactions at equilibrium, the concentrations of reactants and products aren't changing. So their ratio is constant. Okay? And this ratio just depends on the chemical reaction you're doing, but this is just some number. Remember, the lines were flat. They weren't changing. This is just some number. Their ratio is constant. We could kind of characterize this reaction by something called its equilibrium constant. We call that KEQ. I'll talk about where that 2 comes from in a moment. No matter how much NO2 you start with and how much NO4 you start with, at equilibrium, this equation will always hold. It's just a fundamental property of nature to have that ratio. Where this comes from, and we don't go into all the details. If you guys ever change your major to chemistry, like I'm trying to convert some of you guys to, but health science is a wonderful field also. Go where your heart is, right? If you do a job you like, you never have to work a day in your life. I can't believe I get paid for this. Come in here and have fun with you guys, get paid for it. So, but if you decide that chemistry is there, you'll go into the details of where this comes from. It all comes back to why do you think a system exists in the state it exists? I've told you the answer to this.
Because everything wants to be as low energy as possible.
Low energy as possible. There's a certain energy associated with how much NO2 you have in a container and how much N2O4. And the system will exist at whatever the lowest energy is. And there's a relationship between the equilibrium constant and remember that the energy, we call it G, the free energy, there's a relationship. So that's where that comes from. Let's continue though. For this reaction, how do you get this number? You get it experimentally. People make these measurements. For this reaction, that number happens to be 4.6 times 10 to the minus 3 molar. You don't have to remember that number. There'll be about 3 equilibrium constants I'll want you to know over the next couple chapters. I'll let you know which ones I want you to know. That was the equilibrium constant for that particular reaction. Let's talk about in general for any chemical reaction. Here I have the general form of a chemical reaction, right? Molecule A reacting with molecule B to produce molecule C and molecule D. Those lowercase a, b, c, and d, those are the stoichiometric coefficients, right? Those are the numbers we use to balance the equation. So we have some number of A reacting with some number of B to produce some number of C and some number of D. This is supposed to represent the general form of a chemical equation. I chose to make 2 reactants and 2 products. It could have been 1 reactant and 3 products. It doesn't matter. General form. Reactants over here, products over there. I'm just going to get to the end result, but you could show that for any chemical reaction, because of balancing the mass, the stuff Lavoisier started, this is called the law of mass action. For any reaction, we could write this equilibrium constant expression. What you saw on the previous slide was this equilibrium constant expression for the particular reaction, N2O4 going to 2NO2. I'll go back a slide. Remember I told you I'd tell you where that 2 came from? That was the 2 NO2s. This is called the equilibrium constant. These are the concentrations raised to their stoichiometric coefficient power. Those brackets mean concentration in units of molarity, moles per liter. When you write the law of mass action, you put products on top, reactants on bottom. However, here there's 2 products, 2 reactants. However many there are, put the products on top, reactants on bottom. Why that is, that has to do with our convention of going back to energy. We called positive energy when you put energy into a system, negative energy when you remove energy from a system. That's why it turns out that products are on top, reactants are on bottom. I don't expect you to say, oh, I see, I get the math right away, but it can be shown that it's beyond the scope of this class. If you're interested in it, talk to me in office hours. If you're interested, you're going to be that person who might change your major. Beware. When you're writing the law of mass action, pure liquids and solids don't appear in it. So if you see a reactant that's a pure liquid or solid, you don't write it in here. Why is that? Let's say you have a pure liquid. Does it make sense to talk about the concentration of a pure liquid or a pure solid? So we don't put them in there. You could think of we don't put them in there, or you could think of they have a value of 1, however you like, but they don't appear in there. Each chemical reaction has its own equilibrium constant. These values themselves for a particular chemical reaction vary with temperature. Now, we're not going to worry about the temperature dependence in this class. We'll just assume we're given an equilibrium constant, we're asked a question, they're talking about that equilibrium constant is at the temperature in the question. Let's do an example together of writing the law of mass action, and then I'll have you guys do one. So for this example, balance the reaction and then write the corresponding equilibrium constant expression. So you guys are pros now at balancing chemical reactions. Okay, so there it's balanced. Now we're going to write the law of mass action. We're going to put the concentration of the products on top, raised to their stoichiometric coefficient power. And on the bottom, we're going to put the concentration of the reactants raised to their stoichiometric coefficient power. In this case, it's 102, so that will be raised to the first. We don't have to put to the first. So we write this. Products over reactants. Hi, I'm Dr. Jim Zoval. If you like this video and you like to get the entire course or just some of the chapters on video, I have the entire course in video lectures at the website you see on the screen right now. They're available on demand. The period of the rental is for a full year, so you'll have this video through the entire course. You could watch it as many times as you want, whenever you want. Happy studies.